Hello folks, welcome to the mining match. Welcome to the mining match. Today, first of all, we're gonna start by mentioning our sponsor, Spanomine. If you are in the mining industry, you speak Spanish, or you are working in Latin America, you should join Spanomine. They offer professional development and connection in the Latin American community. I'm going to start by saying one word, ore. If you are a miner, you know that ore means money. And ore, you have to know its properties. Because the better you know the properties, the better you can maximize profit. Today, our guest speaker, Jonathan Gibson, will tell us more about this by how we do a practical application of geometallurgy. Hello, John. How are you today?
I'm good, Alain. Thank you very much. Yourself?
Yes, thank you. I'm happy to have you, and please go ahead. It's all
Okay.
yours.
All right. I'll just start sharing my screen here.
Please maximize. Yes. Now it's perfect.
Okay, perfect. Good afternoon, everyone, or evening or morning, depending on where in the world you are. As Alain said, my name is Jonathan Gibson of OptiMineral, and I'm here to talk to you about understanding ore, looking at practical applications of geometallurgy. So the agenda today, we'll do a quick safety share, which is pretty much industry standard in the mining business because safety is our most important metric. Then we'll get into an introduction to geometallurgy and mine-to-mill optimization. I'll cover some guidelines for building, learning, and applying geometallurgical knowledge. And then we'll finish up with mine-to-mill roadmap with some examples of some of the test work you can do. And then, of course, what's most important, closeout discussions. I'd like some feedback, some more discussion, sharing of ideas, hopefully at the end. So the safety share, at least in Canada here, we're transitioning into the summertime. Probably a lot of folks moving their winter stuff into storage and their summer stuff out, and vice versa, depending on if you're the other side of the world. Big thing when doing this is to employ good lifting practices. So lift with your legs, not with your back. Try to avoid twisting and turning when you have a large load, and never hesitate to ask a friend if you have a pretty hard task ahead of you. Now let's just kick right off. So geometallurgy is the study of chemical and physical characteristics of your ore. It's like here, I just need a, okay, there we go. I can see better now. And then looking at the processes of separating the minerals themselves, or what we term as flow sheet. And mine-to-mill optimization is taking that knowledge between those processes from the ground all the way to the plant and looking for opportunities to improve those interactions. The mine mill optimization in itself is more of a philosophy. If we were to put a structure on it, I would argue that one of the best structures would be the DMAIC approach, where you define, you measure, analyze, improve, and then ultimately control some of the KPIs you're looking at targeting and making changes to, or key performance indicators. My picture here says control. I like to say continuous improvement myself, because ultimately perfection is not an endpoint, it is a journey. So the process of mine-to-mill, like I said before, it's a philosophy of collecting data, building your knowledge, and making hypotheses and testing them out and validating, and then ultimately implementing certain applications of this newfound knowledge in a safe, practical, and rigorous way. Rigorous being that sort of sustainability control component. A successful strategy will employ multiple departments. So mainly geology at the front is the easiest one to target, right in the from the core shack to the beat, as well as in engineering, how they're designing their blasts, whether it's a bench on surface or if it's a stope underground. Um, how you control things like dilution, overbreak, underbreak, all will impact how the ore is sitting on surface and being fed to the mill. You're also going to involve people at the mill itself in the metallurgical department, operations, the guys who are actually the boots on the ground. You'll be talking to miners, millwrights, sometimes truck drivers and guys on dispatch. And ultimately also you'll be sending a lot of your test work to labs, so whether internal or external, and then much more in between. Now, in the current trend right now is big data. Everyone loves the word big data, machine learning, Internet of Things. With a lot more data endpoints and repositories of vast amounts of data, there can be tendencies to see correlations and make quick assumptions, but correlation does not imply causation. I've just taken something I pulled from the internet here. This is people who have drowned in a pool compared to films Nicolas Cage has appeared in. And as you see, it's very well correlated, however, not relatable. One of the other terms I like to say is, a tuna sandwich or a ham sandwich in the lunchroom is may show that you pour more gold, but you're going to have to support that support that assumption with a lot more than just a couple data points. Also, is sampling error, garbage in, garbage out. One of the big things you want to do when you're taking a selection of a greater population and reduce that size is that you maintain what we call representative integrity. Sampling in its own right is an art form and a field of study that we could get into quite in depth and detail. However, for the sake of simplicity, just be mindful of the way you're sampling, especially things like gold, where you have a large density difference between gold and, say, your host rock when it comes to density and natural separation and segregation, as well as looking at your measurement systems themselves. Assay labs do have their own inherent gauge error. Operators, when they take samples, have their own error. Every time you have sampling points, you will have you will have error. It's important to define the amount of error you have. Measurement systems are like rulers when you're building a house. If you have change in what you define as distance as you're building it, it's going to be unstable, as is your mine-to-mill program if your measurement system is not locked up and tightened up. So when you're looking at ore, a big thing is to understand your impurities. I'm going to use pyrrhotite as an example. Pyrrhotite is an iron sulfide gangue mineral. It's known to contain nickel, so it can give you false reporting of nickel grade when subjected to just simple ICP analysis. You can define pyrrhotite itself as a different species. If it's monoclinic in the structure, it can be magnetically separated. However, if it's hexagonal in structure, it's non-magnetic, and you have to maybe look at things like chemical depressants like sulfite to keep it in the tails where it belongs. Some other things you can do to liberate, say in this case, pentlandite from pyrrhotite is finer grinding or regrinding if it's say a rougher con or a concentrate intermediate, as well as looking at your material handling, maybe changing that up, whether it's a blending strategy. What we also see is the more pyrrhotite oxidizes, the more floatable sometimes it can become, or the more disruptive it can become. And also as it oxidizes, there's also known as what's termed self-heating. So there might be some issues there as well. Understand the process. So the classic one I like to say is millerite. This is also in base metals, and in this case, copper nickel areas. Millerite is on a atomic scale or chemical formula scale, very high nickel per ton of that mineral compared to pentlandite. Pentlandite is a nickel iron sulfide, whereas millerite is just a straight up nickel sulfide. And it's great when you see it underground because you think you have a very high percent nickel in your ore. However, when you work on the mill, millerite is extremely floatable. If you're employing a xanthate sulfide flotation circuit, the millerite will actually float with your chalcopyrite and your copper nickel separation. So what starts out as, yay, we got really high grade nickel, let's take it, to the other side, oh no, there's millerite in our process, it's polluting our copper con, and you end up paying a penalty on that concentrate as opposed to reaping the benefit of a higher nickel grade. Also is to understand the ore. I'm going to apply my own project that I was growing with some partners. This is in Vohamar, Madagascar. We were looking at heavy mineral sands where specifically around ilmenite and magnetite. Initial ICP analysis showed us that we had really good iron at around 45%. Our titanium was quite high at 12 to 14%. But when we started doing more bench scale test work as well as electron microscopy up in the top corner, we found that actually the ilmenite was banded with magnetite and what's called titanomagnetite. And we could only achieve a maximum with gravity and magnetic separation, about 30% TiO2. And commercial grade, we want to get around 50%. So we never really reached that when that was our focus. However, when we went back to the drawing board, we found that a local smelter could take the high grade heavy mineral sand on its own as 30% of the feed, 70% HMS1 scrap, and they could basically do their pours the way they needed to get a spec they needed to make rebar. So it was one of those, it went from a high to a low to a recover to a high by understanding our ore stream. And how, and basically right down to the electron microscope level, how we can look at benefits and advantages. So as we were discussing before, stage one for mine and mill approach is looking at understanding your feed composition, whether it's your ore, your process, or your impurities. Looking at taking that knowledge and executing based on that knowledge. So you can look at pre-concentration, you can look at raw management of blending strategies, you can look at things like better blasting practices and reducing the transfer sizes, as well as maybe other physical or chemical treatment methods. And then lastly, stage three is kind of taking your whole life of mine plan and then doing R&D around new ore streams, how it's going to impact your mill, trying to find specific recipes perhaps that might give you the best performance. So the examples, the top right screen, we've head grade recovery curve is one of the foundationary relationships you want to know first and foremost before moving into other parts of mine and mill optimization. Your head grade recovery curve is ultimately the higher grade you're feeding your mill, the higher performance you would expect or higher recovery you would expect. Just to wind back the clock a little bit, when we were talking about pyrrhotite, I had mentioned that it might contain nickel. So if say 10% of your nickel is embedded in your pyrrhotite, and you have a really good pyrrhotite rejection circuit, when you're looking at your head grade recovery curve, it's asymptotic. You have like a maximum performance you're ever going to get that the ore will give you, and then there's the capabilities of your plant itself. And if your 10% of your nickel is tied up in the pyrrhotite, and you're rejecting your pyrrhotite, your theoretical maximum is already starting at 90% recovery. So it's unfair to expect any more than that from your mill. Also, it's unfair to just try to lump your mill into one data point of say 90% recovery, which I've seen with many clients. Again, it's important to have a firm understanding of how grade will impact your mill performance, and then set your expectations to that. I had mentioned last week, megatons over megawatts. Bigger blasts will improve your fragmentation and your blast size. When you have better fragmentation, larger blast size, or volume, your oversize is normally your extremities or the perimeters of your blast. The more you allow the perimeter to affect your overall block that you're taking, the more oversize you'll see. Also, if you have better fragmentation, you get better shovel rates, you get more efficiencies in your material handling. And what we also did find is it was indicating better recoveries, lower mill power draw, as well as just overall performance. There's also, with blasts, you want to take precise blasts as well. If you're underground, perhaps you want to protect a hanging wall or footwall, or what we term as breakage. We want to break before we compromise a structure that we don't want failing. So that could be, again, footwall or hanging wall, or that could be the backfill in between stopes. You want to contain your blast, but at the same time, if you also are employing like an ore pass, you want to set your design criteria of your blast such that your fragmentation is going to give you a fine enough size distribution that it will flow well in your ore pass itself. Lastly is one of my favorite things to do. It's a comminution trade-off. First, you do want to understand how your pay metals liberate, or a mineral liberation analysis, as it's called, but also throughput. If you want to improve your throughput, this is just showing in the bottom right corner, different options that were on the table based on, and then just tying that into CapEx, OpEx costs. So something simple as tightening up your jaw, the jaws of your initial crusher might produce a small improvement to be allowed to take on more feed. But also you might see that if we spend an extra amount of money to bring in some pre-crushing, that might have its own sort of trade-off, and then ultimately a bigger capital expense of perhaps mill upgrades, like an additional SAG mill or a grinding circuit. But these are all sort of feeding sort of trade-offs, and normally, based on my experience anyway, a lot of the bottleneck for throughput initially is around the grinding circuit, especially as we're finding ore is getting more complex and harder and deeper. That basically is it. A little bit about myself. I'm a mining and mineral processing engineer. I've got a little bit under 15 years experience. I've been about 13 different countries last time I counted. Many different capacities and roles. I've worked in open pit and underground mines, labs, boardrooms, core shacks. And clients include mining companies, engineering firms, and other consultant types, as well as investment banks for looking at due diligence studies. So this is just a little bit about me and some of the work I do. I was really hoping to get this done fast so we can actually more just discuss ideas and perhaps certain characteristics of ore that people just want to unpack with a larger group. Anyways, thank you for your time, and yeah, hope you enjoyed my presentation.
Thank you, John. All right, so we're gonna open the microphones so people can unmute. You guys in the YouTube channel, the program has ended. Thank you very much for attending. Goodbye.